Hello and welcome everyone. Today's topic is neutron stars. But before we get into that, let us have a look on question of the week. The question of the week is how will you see an object falling into a black hole? Assume yourself as an observer and an object is falling into the black hole. Comment your answer in the comment section. The answer will be discussed in my next video. Now without any further delay, let's get started. So, what are neutron stars? Neutron stars are the densest objects in the universe excluding black holes. Any main sequence star with an initial mass of above 8 times of our sun has the potential to produce a neutron star. Any star can hold their shape because the radiation pressure originating in the star and the gravitational force are in equilibrium. As the star burns out all the nuclear fuel, the iron-rich core remains, and as there is no radiation pressure to neutralize the gravitational force, the star starts to collapse, and the pressure on the core increases. When the mass of the core exceeds the Chandrasekhar limit, that is 1.4 times of our sun, there is a violent explosion known as supernova, and a flow of high energetic plasma is released, leaving a compact core behind. After the explosion, the core collapses further and gravitational force surpasses the electron degeneracy pressure. When this situation arises, the electrons are captured by the protons of the nucleus, forming neutrons. These cause the neutron degeneracy pressure, which counters the further collapse of the core. If the mass of the core is equal or more than 3 solar masses, then even neutron degeneracy pressure cannot hold the pressure and it becomes a black hole. Neutron stars are so dense that a teaspoonful of matter weighs billions kg. On a light note, scientists think that the matter inside neutron star is in a form called nuclear pasta. Inside neutron stars, the competition between the forces leads to the formation of variety of complex structures of neutrons and protons. Astrophysicists call these types of structures nuclear pasta because the geometry of the structures resembles various types of pasta. But what makes the neutron stars the best? From gravitational wave detection to measuring time, there are various applications of neutron stars. Neutron stars are basically physics labs providing extreme conditions such as deep gravitational potentials, densities exceeding nuclear density, magnetic field strengths as high as B equal to 10 to the power 14 or even 10 to the power 15 Gauss. There are mainly two types of neutron stars, magnetars and pulsars. A magnetar is a type of neutron star believed to have an extremely powerful magnetic field. They are so destructive and violent that atoms get shredded when it is within 1000 km of it. Like earthquakes, magnetar experiences starquakes. Starquakes triggered on the surface of the magnetar disturb the magnetic field, which leads to extremely powerful gamma ray flare emissions. In 1979, 1998, and 2004, this kind of flares were detected. The active life of a magnetar is short. Their strong magnetic fields decay after about 10,000 years, after which activity and strong X-ray emissions cease. Given the number of magnetars observable today, one estimate puts the number of inactive magnetars in the Milky Way at 30 million or even more. On the other hand, pulsars is the most useful and interesting type of neutron star. A pulsar is a highly magnetized and rotating neutron star. These are fantastic cosmic tools for scientists to study a wide range of phenomena. The light emitted by a pulsar carries information about these objects and what is happening inside them. That means pulsars give scientists information about the physics of neutron stars. Secondly, the most useful characteristic of a pulsar is that its constant angular velocity, implying constant time period. Now, if a pulsar has its one of the jet towards Earth, then the radio pulses would come with constant time gap. Pulse periods can be measured with accuracies approaching 1 part in 10 to the power 16. The accuracy rivals that of the atomic clocks in Earth. Atomic clocks give accuracy up to 1 part in 10 to the power 17, but the problem with atomic clocks is that they slow down and it happens within human lifespan. On the other hand, pulsars are very stable and they can have constant time period for thousands of years. This is why pulsars are the timekeepers of the universe. Thirdly, using the time period method, scientists can measure cosmic distances. The changing position of the pulsar means the light it emits takes more or less time to reach Earth, and thanks to the exquisite timing of the pulses, scientists have made some of the most accurate distance measurements of cosmic objects. Gravitational waves using neutron stars can be detected in various ways. As neutron stars are so compact and heavy, they create ripples in space-time when they collide. These ripples are gravitational waves and can be detected in the labs. On 17th August 2017, LIGO and Virgo detected a pulse of gravitational waves generated from two neutron stars merging together. As neutron stars are plenty in number in our universe, the detection of gravitational waves are a lot more convenient. The neutron star mergers are very special. When two neutron stars orbit each other closely, they spiral inward as time passes due to gravitational force. Depending on whether the mass of the remnant exceeds the Tolman-Oppenheimer-Volkov limit, their merger leads to the formation of either a more massive neutron star or a black hole. If the remnant exceeds the limit, which is 3 solar masses, then it becomes a black hole. The merger releases a magnetic field that is trillions of times stronger than that of Earth in a matter of 1 or 2 milliseconds. These events are believed to create short gamma ray bursts. The mergers are also thought to produce kilonova. A kilonova is a transient source of fairly isotropic longer electromagnetic radiation. Heavy elements are produced and ejected during the merger process. All the heavy elements that we see today came from these kinds of supernova or kilonova explosions. Change in the pulses of a pulsar can depict gravitational waves creating ripples in space-time. As the gravitational waves distort the space-time, the pulses, those were coming from a pulsar with a constant time period, change their timing, and hence they result into the detection of gravitational waves. So this was the neutron star in a nutshell. Thanks for watching. If you liked it, then like, comment and share this video. And to see such videos in future, don't forget to subscribe.